What happens if Earth stops spinning? Earth has been spinning continuously for more than 4.5 billion years. This rotation is so constant that we rarely think about it. Yet it quietly shapes almost every physical system on the planet. Once every 24 hours, Earth completes a full rotation. This motion defines day and night, drives weather patterns, and helps regulate global temperatures. But what if that motion suddenly stopped? Not slowed down, not altered gradually over millions of years, but stopped completely all at once. Using well-understood physical laws, we can trace what would realistically follow. Earth rotates from west to east around an imaginary axis passing through the north and south poles. At the equator, the planet's surface moves at roughly 1,670 kilometers per hour. This speed decreases with latitude, reaching zero at the poles themselves. Despite this extraordinary velocity, we feel no sensation of motion. That is because everything around us, the ground beneath our feet, the oceans, and the atmosphere, moves together at nearly the same constant speed. In physics, constant velocity produces no detectable force. Only changes in motion are felt. This is why Earth's rotation feels no different from standing still. The situation is comparable to sitting inside a smooth, steady aircraft cruising at high altitude. As long as the speed and direction remain unchanged, motion becomes imperceptible. It is also important to clarify a common misconception. Earth's rotation and Earth's gravity are separate phenomena. Gravity arises from Earth's mass and its effect on space-time. Rotation slightly modifies gravity's apparent strength, but it does not create it. If Earth stopped spinning, gravity would remain almost entirely unchanged. In this scenario, Earth's solid crust abruptly comes to rest. However, not everything on the planet is rigidly bound to that crust. According to Newton's first law of motion, an object in motion will continue moving at a constant velocity unless acted upon by an external force. This property is known as inertia. The oceans, atmosphere, buildings, vehicles, and living organisms were all moving eastward along with Earth's rotation. When the ground stops, these systems do not stop at the same time. The planet halts. Everything above it continues moving. The resulting difference in motion between the stationary surface and the still-moving fluids and objects becomes the source of the most immediate and destructive effects. Water has mass, and mass resists sudden changes in motion. As Earth stops rotating, the oceans continue moving eastward at their original rotational speed. Near the equator, this motion is extreme. Instead of a single wave, the oceans experience a massive redistribution of water across the planet. Entire bodies of water surge forward, driven by momentum rather than seismic activity. Coastal regions are inundated within minutes. Water flows inland with immense force, overwhelming natural and artificial barriers alike. Mountain ranges do not stop this movement. They redirect it, forcing water through valleys and across plateaus, carving new paths and stripping away soil and sediment. Over time, this process would dramatically reshape coastlines, continental shelves, and ocean basins, all without any tectonic activity. The atmosphere responds in a similar way, but on a global scale. Air near the equator continues moving eastward at speeds exceeding 1,000 kilometers per hour. This creates sustained, planet-wide winds far more powerful than any hurricane or tornado ever recorded. Unlike short-lived storms, these winds persist until friction with the surface and terrain gradually dissipates their energy. The effects would be catastrophic. Forests would be flattened. Loose soil would be lifted and transported across continents. Structures not engineered to withstand extreme aerodynamic forces would collapse. Eventually, the atmosphere would slow and settle, but only after widespread global disruption. Earth does not explode. The planet does not tear itself apart. Its gravity remains nearly unchanged. The core continues generating heat through radioactive decay and residual formation energy. There is no sudden shutdown of internal processes. The devastation comes entirely from momentum imbalance, not structural failure. Once the oceans and atmosphere lose their excess motion, Earth reaches a new mechanical equilibrium. The planet is intact, but profoundly altered. Without rotation, Earth no longer cycles between day and night every 24 hours. Instead, one hemisphere permanently faces the sun, while the opposite hemisphere remains in constant darkness. A single day now lasts one full year. Roughly 6 months of continuous sunlight, followed by 6 months of uninterrupted night. On the sunlit side, solar energy accumulates relentlessly. With no nighttime cooling, surface temperatures rise steadily, potentially exceeding the boiling point of water in many regions. On the dark side, the absence of sunlight allows heat to radiate into space. Temperatures fall dramatically, freezing oceans, soil, and atmosphere alike. Earth's rotation plays a crucial role in driving atmospheric circulation. It influences trade winds, jet streams, and ocean currents through the Coriolis effect. Without rotation, these systems weaken or reorganize entirely. Heat transfer between regions becomes inefficient. Warm air rises on the sunlit side but struggles to circulate globally. Ocean currents slow, reducing their ability to redistribute thermal energy. The result is a planet divided into extreme climate zones, with sharp boundaries between intense heat and extreme cold. Earth's magnetic field, generated by motion in the liquid outer core, would not vanish immediately. However, long-term changes in planetary dynamics could weaken it over geological timescales, increasing exposure to solar radiation. Life on Earth evolved under stable, repeating cycles of light and darkness. Plants rely on predictable sunlight to drive photosynthesis. Animals depend on ecosystems shaped by seasonal and daily rhythms. With extreme temperature contrasts and prolonged darkness or heat, most ecosystems collapse. Photosynthesis becomes unsustainable across much of the planet. Food webs break down. Species unable to adapt rapidly face extinction. This is not instantaneous, but it is unavoidable. Human survival would be severely limited. Modern agriculture depends on predictable climate patterns and solar cycles. Without them, large-scale food production fails. Stored resources provide only temporary relief. Energy demands increase as heating and cooling become constant necessities. The most survivable regions would likely lie near the boundary between light and darkness, the twilight zone, where temperatures are relatively moderate. Even there, survival would require advanced technology, careful planning, and strict control of resources. Earth's rotation is one of several finely balanced factors that support long-term habitability. Many known exoplanets are tidally locked, always presenting the same face to their star. These worlds often experience permanent extremes, making complex ecosystems unlikely. Earth's steady spin distributes energy, stabilizes climate systems, and supports biodiversity. It is not dramatic. It is not visible, but it is essential. Earth does not need to stop spinning for us to understand its importance. By examining what would happen if it did, we gain insight into how delicately balanced our planet truly is, and how many invisible forces quietly sustain life every day. If you found this exploration meaningful, you may consider liking the video or subscribing for more science-based perspectives on our universe.